Now let's turn and take a look at coordinate systems. Coordinate systems provide a means to describe location using pairs of coordinates. And one very simple type of coordinate system that we have is what's called a Cartesian coordinate system. A Cartesian coordinate system is used for locating points on a flat two-dimensional map, and the coordinate values represent the distance from the grid origin, which is 0, 0. In this cartoonish example on the right, showing Australia, the origin is down here at 0, 0, and we have values increasing on the y-axis and on the x-axis away from that origin. In cartography and surveying, the x-axis coordinates are referred to as eastings, and the y-axis coordinates are referred to as northings. If you want to find the shortest distance in a planar Cartesian coordinate system, you would calculate what's called Euclidean distance, which measures the distance between two locations or points. But we have to be careful because although this is very easy to calculate, it's not always the shortest geographic distance. And the reason for that is because when we project a three-dimensional globe onto a two-dimensional surface, the straight lines on that two-dimensional surface are not necessarily going to be representing great circles, which you will recall is the shortest geographic distance on a globe. We calculate Euclidean distance by taking the squared differences between the two coordinate pairs. So we difference the two x values and square that difference to make it a positive value, and then we take a difference between the y values and we square that difference to make it positive, and then we add those values together and we take the square root of that sum. So in this example, we have x value of 2 minus y value of 4, and we square that, and a y value of 3 minus y value of 2, and we square that. Add those two values together and take the square root, and that gives us 2.236. Now the units of this coordinate system are undefined and arbitrary, but any calculation of Euclidean distance would be in the same units as the map. So we would say this is 2.236 units of distance, could be meters, kilometers, between those two coordinate pairs. We can also define Cartesian coordinate systems in three-dimensional space by adding a z-axis. When we add a z-axis to a plane that's defined by an x and y-axis, then we can start to describe height of features, and we can also describe elevation. So three-dimensional Cartesian coordinate systems can be useful, but they're only useful at local scales. So this image on the right shows why we cannot use Cartesian coordinate systems at a global scale. These three-dimensional Cartesian coordinate systems have been oriented perpendicular to the spherical Earth, and so local Cartesian coordinate systems are useful when you're trying to find direction locally, but they're obviously not that useful beyond a local scale. If you wanted to find position at a global scale, you would have to use what's known as the geographic coordinate system. The geographic coordinate system is that graticule of lines of longitude and latitude that define position on a spherical Earth. The origin of this coordinate system is the intersection of the equator and the prime meridian, which are the two axes represented as x and y, where the x-axis is the axis of latitude and the y-axis is the axis of longitude, intersect, gives us the origin for our graticule, which again is roughly right off the coast of Africa here at 0, 0. Latitude and longitude are angles from the center of Earth relative to an arbitrary origin, which gives us the intersection of the prime meridian and the equator. The units of latitude and longitude are always in degrees or grads, but what's important to remember here is that the geographic coordinate system is not a map projection. So the geographic coordinate system is a three-dimensional coordinate system for Earth. The map projections that we looked at in the previous video also have their own coordinate systems, but those are what are called projected coordinate systems. Anytime that we project the three-dimensional Earth onto a two-dimensional page, we are generating a two-dimensional projected coordinate system. Now I want to walk through one example of a projected coordinate system that's widely used around the world called the Universal Transverse Mercator, or UTM. UTM is a cylindrical projection where the cylinder has been turned on its side. So for that reason, we call it transverse. The tangent of this cylinder is now running north and south between the north and south poles, as opposed to a regular Mercator cylindrical projection where the tangent would be the equator, running east and west. The UTM projection is actually 60 different projections. So instead of just being this one cylindrical projection that has one tangent, we actually rotate this cylinder around Earth 60 times and we generate 60 different zones. And each of these zones is divided by 6 degrees of longitude. 6 zones times 6 degrees of longitude gives us 360 degrees of our spherical Earth. Now I just want to come back to our 3D calculator and show you what a transverse Mercator looks like. Again, this is a cylindrical projection, but the cylinder has been turned on its side relative to the axis of rotation of Earth. The axis of rotation is this imaginary line that connects the North and South poles. And so this cylinder is basically perpendicular to that axis. An interesting property of orienting the cylinder transversely like this is that the tangent is no longer at the equator like a regular Mercator projection. In fact, the tangent is perpendicular to the equator and runs through the North and South poles. And so for that reason, the UTM projections do not have parallels running east and west, and instead they have these north to south lines of longitude. This has the benefit of minimizing the distortion that is occurring along this tangential line for the cylinder on both hemispheres of the sphere. So you get the least amount of distortion down the center of this north-south center line of the map projection, and you get more and more distortion as you move east or west of this line. So for this reason, each UTM zone is limited to 6 degrees of longitude in width. And this is simply to maximize the benefit that we get from this transverse cylindrical projection. Here's another example of a UTM zone that's being highlighted in yellow that runs through Europe, showing the Tissot's indicatrices if we map the rest of the world using the projection for this UTM zone. It's kind of confusing, but remember that each UTM zone is a different map projection representing a different slice of Earth, a different range of 6 degrees of longitude, and with a different central meridian. We can map the entire world in any UTM zone, but this figure shows how distorted the rest of the world becomes when you are mapping outside of your local UTM zone. You'll notice that the indicatrices are perfect circles along the central meridian of the UTM zone, which is what we expect. This is where the transverse cylinder is tangential to Earth. In Canada, we have 16 UTM zones that cover the entire country. In British Columbia alone, we have 6 UTM zones that cover all of the province, which is a pretty wide province longitudinally. So we span from zone 7 to zone 12. There's a tiny little fragment of BC down here in the south that's in zone 12, and this tiny little fragment that's in zone 7. So we have 6 zones that span our entire province. And Vancouver down here is in zone 10. So if you're mapping any data in British Columbia, most likely you're going to be using zones 9, 10, or 11 for that, cover most of the province. Each UTM zone has a central meridian, which defines the center of the projection longitudinally. We conveniently use the equator to define the center of the projection latitudinally. The intersection of the central meridian and the equator marks the origin for the coordinate system of any map projection. So let's take a closer look at how this works with the UTM projections. The origin of the coordinate system is mathematically defined as 0, 0, which means there are positive coordinate pairs in the northern and eastern hemispheres and negative coordinate pairs in the western and southern hemispheres. The equator has a northing value of 0. Anything north is positive, anything south is negative, and the central meridian has an easting value of 0. So anything east of that is positive and anything west is negative. By convention, the UTM projections use what's called a false origin to ensure that both easting and northing values are always positive. This involves adding a constant value to each easting coordinate and a constant value to each northing coordinate. So UTM zones are 6 degrees of longitude wide, which is approximately 1,000 kilometers or 1 million meters. So if we add 500,000 meters or half the width of the zone to all easting values to generate what are known as false easting values. This just ensures that all of our easting values will always be positive. To further complicate matters, the convention is to also split UTM zones into the northern and southern hemispheres using the equator. This actually results in UTM zones north and south. So in Vancouver, we are in UTM zone 10 north. Our southern counterpart, UTM zone 10 south, represents everything within the same 6 degrees of longitude that we occupy, but south of the equator. Since only values south of the equator are negative, we only need to add a constant value to southern UTM zones to make the northings positive. So the distance between the north and south poles is approximately 20 million meters, as we saw from the calculations of Eratosthenes. Now we take half of that value, 10 million meters, and we add it to all of the coordinate values in the southern hemisphere. This has the result of producing UTM coordinates in the southern zones that are always positive. And for this reason, we call those coordinates false northings. So with false northings, coordinate values in southern hemisphere UTM zones now range from 0 meters at the South Pole to 10 million meters at the equator, right? That's half or roughly a quarter of the circumference of Earth from pole to pole. Confusing, right? You might be asking yourself, why do we do this? It's mostly out of convenience and convention to not have to deal with negative numbers in our coordinate values. Also, UTM zones are meant to map things accurately at a local scale, hence why we divide UTM zones into north and south. Now let's take a practical example of the Forest Sciences Center building here at UBC, which is about 18 kilometers west of the central meridian for our UTM Zone 10 North. The true easting value of the forestry building is negative 18,000 meters, right? We're 18,000 meters to the west of the central meridian. But if we add 500,000 meters to our negative 18,000 meters, then we end up with our false easting value of positive 482,000 meters. The building is also about 5,480 kilometers north of the equator, so our false northing value is 5,480,000 meters. And that comes from the fact that we are that many million meters north of the equator. So the coordinates of the Forest Sciences Center would be represented as 482,000 meters easting by 5,480,000 meters northing in UTM Zone 10 North. Just know that when you're viewing UTM coordinates in GIS, you are almost certainly looking at false eastings and false northings. Creating the coordinates this way also makes it easy to know how far you are from the South Pole or from the equator, and how far you are from the edge of the map projection. Keep in mind that these are coordinates in a two-dimensional projected coordinate system. They are not latitude and longitude values that correspond to the geographic coordinate system of a spherical Earth. So in summary, map projections are these formula that allow us to translate from three-dimensional coordinates to a two-dimensional coordinate space. And this is ultimately a necessary evil because, like any other model, map projections are simplifying and abstracting reality in a way that is convenient and useful for us. So we use map projections in different applications. So you have to be mindful when you're choosing a map projection for what your application is. Are you trying to map things over a very large area at a very large scale? Are you trying to preserve area or shape or distance? Those are all considerations that go into your thinking when you're thinking about what type of map projection should I be using for a particular application. And finally, we looked at the Universal Transverse Mercator, which is probably the most widely used map projection or set of map projections out there. And most likely you'll come across any kind of data that's published online will be in a UTM map projection. So that's all for now. Thanks for watching.